Alright, so today we're looking at section 6.1, inverse trig functions. So what we're trying to do here, our objective is finding exact values for radians and degrees, finding inverses that is, and then find approximate, inverse values for radian degree angle measures as well. So what we're looking at with inverses. So remember, Algebra 2 talked a little bit about inverses and the inverse functions. And basically with an inverse function, you were taking your x and your y values and you were switching them around. It's where your y's became x's, x's became y's, and how that affects your graph. So as a trig function, what we're looking at here, this is a normal graph. Hopefully we can recall a sine. So then when you switch the x and the y values, what happens is then you get a graph that looks like this. One of the problems that we'll get into here is as a function, if you do the little vertical line test, this thing fails a vertical line test because the vertical line intersects the graph on several parts, not just one. So what we're going to get into here in a bit is discussing how to help us pass the vertical line test for some of these graphs. We're going to essentially cut the values out so that you're only looking at a graph like this. So now it would pass a vertical line test. Alright, so what this allows us to do, find an angle measure when given a specific trig function value. So one thing you want to do is we'll have notes packet associated with this lesson with all of this on here, but take a look at this table. What I have here is a unit circle picture. What I mean by that is you're basically, as I said before, we're cutting the graph down the size so that it passes a vertical line test, so it can be a function. We're going to cover what parts of the unit circle each of these inverse functions will give you answers in, meaning it'll tell you where it's possible to get a solution, where it's not possible to get a solution. So with sine, it's saying our sine is going to be between 90 and negative 90. So on the unit circle, what we're looking at here is that sine, or inverse sine, is going to give you values from here to here. So this part of the unit circle, where that's a positive, and that's where sine is negative. So if you're taking the inverse of a negative answer, it's going to give you an angle measure like negative 30. If you're taking an inverse of a positive exact value, then it's going to give you a positive answer here like 30, 60, 90, etc. Okay? Cosine. Cosine inverse finds solutions in this range of the unit circle where this is positive and this is negative. Tangent. Now one thing you notice is a little bit different about tangent is it no longer has those less than or equal to values. It's just less than. So it means there's going to be a hole at 90 and negative 90, and it's going to cover all the values in between those, where once again 0 to 89.99999 is positive, from positive there, negative down here. Alright, cosecant. Once again, you'll notice it has another little hiccup there to where it has a hole, and that's at 0 degrees. So cosecant has a hole at 0 degrees, and that's because of that asymptote. And then you get in that general region. Okay? And let's see here. We have secant. Secant has a hole at 90. Looks like that. And then cotangent gives you angle measures as solutions in that range, where these are all positives, negatives. So, looking at these little picture things are useful to know because it's a whole lot easier to remember this than it is to remember all of this domain and range and all those specific numbers. So what we're going to do here is find an exact value for arcsine of root 2 over 2. Now, one thing to keep in mind, arcsine, what that refers to, that's the same as sine inverse. It's kind of You see it more often in older texts, but it is the same thing as a sine inverse like this. So first thing we want to do is we want to make sure that the value we're given meets restrictions. What that basically means is, can sine equal root 2 over 2? So we know sine values have to be in between -1 and 1. Root 2 is in between those, so it works. So this is met. So now if it does, we need to find the angle measure that matches, okay? So then inverse sine of a positive, from the little unit circles before, we said that inverse sine is positive here, negative there, and inverse sine does not cover those regions. So we draw out our nice little triangle. Since it is positive, it's going to be out here. So we're looking for this angle measure. So we can draw a little reference triangle. Now, if you remember root 2 over 2, if you unrationalize that, that's 1 over root 2. It's probably easier to notice what the triangle is if you think about it in its unrationalized format. So, two ways to do this. One, I'm drawing a picture here just so you can kind of see. This is a 45, 45, 90. So, theta would equal 45 degrees. Your life is a lot simpler if you have all those values memorized, which a lot of you don't. But knowing the basic exact values once again and memorizing, as I've said repeatedly, is super helpful, including this. One thing again, in degrees, our answers in degrees, but remember from the previous slide here that we're not, for inverse sine, you're not including anything in this range. That's not used. So no angle measures that can pass through there can be used. And also remember, so you're going to get one solution. You're either going to get one answer here or one answer where it's negative. You're not going to get two answers like what we've had in the past. All right, moving on. Find some more exact values here. Leave your answers in radians. So draw it out. Hopefully, go back. You'll notice that cosine is positive here, negative there, and doesn't use any of that. So we know we're in this general region. That's our answer for theta. Theta goes there. So we draw a nice little triangle. -1, 2. That would then be a root 3. So 30, 60, 90 says this is 60, which means that whole thing has to equal 120 degrees. But the answer is supposed to be in radians, so it's 2 pi over 3. On our quiz, a lot of it's going to tell you to put your answers in radians, so you need to know these conversions. You need to be able to do this and figure out 120 is 2 pi over 3, etc. Otherwise, you're in some trouble for the quiz. Alright, cotangent. Cotangent, similar to cosine. Same general area, so it's going to be positive. So the inverse of a positive is going to be in there, and inverse of a negative is in quadrant 2. What we have here is we're taking the inverse of a positive, so it's in this general area. Draw theta. So that's giving us an angle measure. So cotangent is root 3, so that's a root 3. Also remember that you can always put something over 1. So then we know this angle measure opposite of the 1 should be 30 degrees, which once again, hopefully you know your conversions and know that that's pi over 6. Alright, some other things real quick. When using your calculator, take a second to write this down. Pause the video and move it on. Try these plugging your calculator. If you get some really goofy answers, then come check with me in the morning. We'll make sure your calculator is in degrees, not in radians, because sometimes if you're in radians, this will come out to be like 0.6321 something or other. It's something really weird. Make sure knowing this is in quadrant 1, make sure you're getting something that's an angle measure in quadrant 1 and not some really goofy looking decimal. One last thing, with inverse functions, if you compose functions or an inverse function with its standard function, they will a lot of the time cancel out as long as the angle measure contained within the quadrants of both functions exist. And what that means is that this angle measure for cosine has to exist in one of those top two quadrants, because cosine inverse doesn't work down here. So you're doing the cosine inverse of something, of cosine of some angle measure that's in this bottom section, down there. Cosine inverse can't give you that as a solution, and so it won't work. And I'll show you tomorrow more or less how that works, but just keep in mind that a lot of the time an inverse function and regular function, they'll cancel and leave you with whatever's in here. Hope this makes sense, and we'll see you guys tomorrow.